Okay, welcome back. Today, we're going to talk about Chapter 8, which deals with confidence intervals. Now, you'll notice that I have pulled up not only the slides here, but a copy of Google Sheets. You could also use Excel because here we are going to be very technology heavy. If we didn't have technology with us, our best use would be a T table and a Z table. We won't be covering that in this course. So I'll talk you through how to construct these confidence intervals using Google Sheets and talk about what each of these bits means. Before we get into all that, let's talk about what confidence intervals actually are. A confidence interval for a certain distribution, if we know the mean, is a range of values centered around the mean where a certain percent of the values are going to be within this range. So for example, if I have our normal distribution centered at the mean, I might say that I'm looking for a 90% confidence interval. So what we're looking for is 90% of the values to be in the certain range. We've talked about, in terms of for a normal distribution, what that would end up looking like. And we know we have our empirical rule. So if it was 68 or 95, we know exactly how many standard deviations it would be. If it's a number that doesn't line up nicely, we know we'll need to use norm inv. In any case, we'll obtain two values. These values we're going to call x min and x max. And this is the top and the bottom of our confidence interval. The distance from the mean to these endpoints is known as the EBM, which stands for the error bound on the population mean. And this is how far off we think our mean might be from the true mean. Typically, we'll be using this approach for a distribution of samples like we talked about last time. And we will say that, well, we took a whole bunch of samples, and this is the range where we're 90% confident that the means will fall. We are using this and comparing it to the true mean to say that we are 90% confident that our mean that we calculated is within this range of what the true mean is. We'll sometimes use alpha as a variable to represent the missing parts. So in this specific example, our alpha would be 0.1 or 10%. 90% is inside the range, so 10% is outside the range. The tails on each side will always have alpha over 2 as the proportion of the data. And that alpha over 2 will show up again, so we'll want to keep that in mind. We'll sometimes call the 90% the confidence level. Or alternatively, simply P. In any case, our alpha and our P will add up to 100% or add up to 1. Let's go through an example of making a confidence interval. We're looking at pizza delivery times. Suppose pizza delivery times are normally distributed. We don't know what the mean is, but we do know the standard deviation. It's 6 minutes. We took a sample of 28 pizza delivery restaurants, and we found that the mean of our sample was 36 minutes. We would like to find a 90% confidence interval. So first thing I'm going to do is I'm going to draw a picture of what's going on. This is the distribution of the sample means. And we're going to say that this is the true distribution centered at some mean we don't know. Compared to our distribution, which has our calculated mean of 36. What we're trying to find is a 90% confidence interval based on our distribution, where somewhere inside there is the actual mean. It's somewhere inside this 90% region. That's going to be our goal. So we're going to be focusing here on the distribution made using our mean and try to tackle what the true mean is going to end up being. So let's just go ahead and record everything that we know in terms of the variables. Our confidence level is 0.9, which makes our alpha 0.1. Our sample size is 28. Our calculated mean is 36. Remember, we don't know the true mean. Our calculated, or excuse me, the true standard deviation is 28. We're going to use all of this information to construct our confidence interval. Now, we did a lot of this last time. We need to find the values that will give us 90% centered in the middle, which basically means there's 5% here, then 90% here, and then 5% here. So we need to find the two values at 5% and at 95%. And we can do this using Google Sheets. Now, there's two ways that we can do this. Way number one is calculate the z-score, and way number two is by calculating the two values using our norm inv. But what I'm going to introduce is the method that we can use with the z-score. And there's a couple of reasons that we're going to want to do it this way, which I'll get to after we go through the example. For this, I want to introduce a term called, or a new function, norm. Let me double check exactly the thing in Google Sheets here. We'll show it off. Normsinv. The decimal place is not included, no dot here. Normsinv of P. What this will do is it will go from a probability or a percentile to a z-score. We also have the function normsdist, which will go from a z-score to a probability. We can use these, or we can use the original of normdist and norminv without the s to skip over the z-score. In this case, the z-score is actually going to end up being more useful, and I'll show you why in a moment. But just keep in mind that the s, you can remember this. This s that's included additionally stands for standard, meaning that instead of giving us out the specific numbers for our distribution, it will give us the standardized z-score, which is just the number of standard deviations. Z-score deals with standard deviations, hence we've got the S for standard. So we're looking for normsinv. It takes just in a probability, so we want 0.05 because we want the number of standard deviations to be at just 5%. And it says the z-score is 1.64. We would call this z of alpha over 2, or the z of 0.05, gave us negative 1.644. We also have the z of 0.95, which we know is going to end up being positive 1.644. Because the graph is perfectly symmetric, on the other end, we will have just the exact opposite. So this 1.644, this is the piece that we need. This tells us the number of standard deviations away that we need to go. Remember, we'll need to calculate the standard deviation for our distribution of means to be the original standard deviation divided by square root n. So that will end up being 28, in the denominator. And the standard deviation we had was 6. That was why I got it wrong, because I wrote down the wrong number. 6 is our standard deviation. So 6 divided by root 28, we might plug that into our Excel calculator. Comes out to be 1.13. Okay, so now we know how many standard deviations it's supposed to be. That's the z-score. We know how big the standard deviation is. That's the 1.13 we just calculated. So the error-bound mean is going to be the z-score multiplied by this new standard deviation. So that ends up being 1.644 multiplied by 1.13. I'm going to change this from 0.05 to 0.95 because it will give us the positive version. And let's add in another column here to label what we're doing. We'll zoom in a little bit. So right here is the z of alpha over 2. And this is the standard deviation for x bar. So here we can get the EBM, which is equal to the z-score, the number of standard deviations, multiplied by how big a standard deviation is. So here we're getting 1.86. Visually on the graph, what that means is we've got the size of one standard deviation and this is 1.64 of those standard deviations, giving us a total distance of 1.865 going in either direction. Therefore, the confidence interval is equal to our calculated mean minus the EBM as the lower bound and the calculated mean plus the EBM as the upper bound. So that will be 36 minus 1.86, 36 plus 1.86, which would be 37.86. Whoops, that will be the upper. The lower would end up being 34.14. What does this mean? We can interpret this. We are 90% confident that the true mean delivery time is between about 34 and 38 minutes, rounding there for the final answer. Let's walk through all of this one more time before moving on. We're given a mean that we calculated from our sample. We know the size of the sample, and we know what the real standard deviation is. What we want to find is a range where we're 90% sure that the true mean is in that range. So what we did is we calculated a 90% interval where we're 90% confident that our that of the values, where we're 90% confident that a sample would fall within that range based on what we calculated from our sample. Using Google Sheets, we were able to calculate how many standard deviations it would be, and we were able to calculate how large each standard deviation was. We multiply these two together to find the error bound, and then we just simply add and subtract this number from the mean in order to give us our confidence interval. Now, because of this formula, the exact same formula that we used, what we can do is we can determine how big our sample needs to be in order to get a certain confidence interval based on what the standard deviation is. Very often, we will know that we want a certain error bound and a certain confidence interval, and we will be asking ourselves, how big a sample do we need for this? So for instance, in this scenario, we're saying that we know the standard deviation for the age of students at a certain college is 15 years, and we want to be 95% confident that the sample mean age is within 2 years of the true mean. We need to know how large the sample should be. Well, we can use this equation. The EBM, we're saying we want that to be 2. The Z is for a 95% confidence interval. That means that alpha is 0.05, and thus alpha over 2 is 0.025. We could plug in to Google Sheets to see exactly what the alpha would be, but we know that this is 95%. This is one of our empirical rules. So the Z of alpha over 2 should be about 2. And we can quickly check that over here. If we take Z of 0.025, that means that we are using norms inf of 0.025. And it gives us out, remember, it gives us out a negative value because it's looking for standard deviations below, but we would simply turn it positive. It gives us out a value of negative 1.96, which is about 2. We could use this number and be more precise, or if we're using our empirical rule, we could use 2. In this scenario, let's just use the approximation of 2, but if we wanted to be more precise, we could use 1.96 instead. We don't know what the sample size is. We're trying to find a sample size. We do know the standard deviation. It's 15. So we can simply plug in 2 is equal to 2 times 15 over root n and solve for what n needs to be. So in this case, root n would end up being 30 over 2, which is 15. And so n would need to be 15 squared, or 225. Simply put, if we would like to be 95% confident that whatever sample we take is within 2 years of the true mean, we should be sure to sample at least 225 students. using this equation, we could move from any one of these to anything else. Typically, it's the error bound, the alpha, and the sample size that we're working with. As a general rule, the larger the sample size, you'll be able to be either more confident or you'll be able to have a smaller range. The range of your confidence interval and the amount of confident that you are is a kind of trade-off. So you can, if you have a same sample size, you can either decide to be more confident with a much wider range, or alternatively, less confident with the skinnier range, which makes sense. The more of the percentage that you take in our distribution, the further out you'd need to go. But if you increase the size of the sample, then the distribution becomes much skinnier. So you can choose to just sample more in order to get a more precise, more accurate results. Now, there's one big problem with what we've been doing up through here. What we've been doing is making assumptions that the actual standard deviation is the same as the one we calculated. And that's just typically not the case. If we find a certain sample, not only is the mean we got from that sample an estimate, but so is the standard deviation. And using the z-score to approximate the number of standard deviations we go out only works well if we're confident that our standard deviation is right. If we don't actually know that our standard deviation is right, using z-score doesn't really make a whole lot of sense. And so we're going to use something called a t-score. We're not going to go into detail at all about why a t-score works. What we are going to talk about is when to use it and what the differences are. A t-score, which comes from a t-distribution, a t-distribution is like a normal distribution, but it is a wider distribution. If this is normal, then the corresponding t-distribution might look something like this. More of the percentage is out at the extremes as compared to a normal, where more of the percentage is centered at the middle. Because this t-distribution is more spread out, it's more appropriate for when we don't know the standard deviation. The percentage is going to be much further away, and as a result, it is going to be a less confident interval. But that ends up being more accurate when we don't actually know the standard deviation. A t-score works the exact same way as a z-score does, but because the standard deviation is an estimate, the t-score is going to end up being a little bit larger than the z-score, giving us a wider interval. There's one other thing we'll need to keep in mind. Remember that when we increase the when we increase the sample size, our normal distribution gets much skinnier. Well, something very similar happens with the t-distribution. We'll have to keep a new term in mind called the degrees of freedom, which is very simply one fewer than the sample size. Long story short, basically, if you knew all of the values except for one, and you also knew what the mean was, or you also knew what the standard deviation was, then you could basically backtrack the formula to find the missing value. And so degrees of freedom is the number of values that you can know if you also know a statistic and still not know them all. And it's always one less than all of them. So that's where degrees of freedom comes into play. We'll need to use degrees of freedom in order to plug into Google Sheets. The last point I'll make about the t-distribution is that when the sample size is very small, the t-distribution is much more spread out than the standard deviation. But as the sample size grows larger, they get fairly close together. Before the days of technology, it was said that 30 was close enough where the t-distribution and the standard deviation for a normal distribution would end up being the same. Now that we have technology and we can quickly do a t-distribution or a normal distribution, we would say that we would care up to at least 1,000. Anything past 1,000, and it probably doesn't matter whether we're using a t-distribution or a normal distribution. But up to 1,000, we do care. In any case, let's go through an example. A study measured how many hours a group of students sleep each night, and we have the results given below. Let's go ahead and copy this down. So 8.2, 9.1, 7.7, 8.6, 6.9, 11.2, 10.1, 9.9, 8.9, 9.2, 7.5, and 10.5. We need to find the mean, the standard deviation, and then use this to create a 95% confidence interval. Now, before we even do anything, we know we're going to need a t-distribution rather than a normal distribution. And the reason we know this is that nowhere in this information does it tell us what the real standard deviation is. We've got a sample. We can find the standard deviation of our sample, but we don't know what the real standard deviation is for all students and how many hours they sleep. As a result, a normal distribution would not be precise enough. So we need to use a t-distribution to account for this uncertainty. So we'll use a t-dist because we do not know the real standard deviation. Here's what we do know. The sample size is 12, which means the degrees of freedom is 11. We can calculate a sample mean and a sample standard deviation. We'll need to use Google Sheets for that. We don't know the true mean and the true standard deviation. Also, we know that the confidence level is 0.95, which means alpha is 0.05, and alpha over 2 is 0.025. We can use all of this information. Now, let's go ahead and calculate some stuff. So I'm going to add an extra column and an extra row so that we can label things. So this will be the x values. We can find the mean. This will be the average of these values. So 8.98. Okay, we can just go ahead and round that to 8.99. Oops, 8.98 actually is more correct. We'll say 2 decimal places is good for now. For the standard deviation, I'm going to remind us one more time how we would calculate it out by hand. But from now on, I will allow you to use the standard deviation function. So let's do it out by hand once, and then I'll show you how the function works. So this would be the first thing we need to do is we need to do the difference from the mean. So that would equal this value minus this value, and we need the $ on the mean, so we know not to change it. Bring that down. Next, we need the difference from the mean squared. So we'll do this times itself. Then we need to do the sum of all of this. Then we will need to divide by n minus 1. And we now know this is the degrees of freedom. So we could divide by the degrees of freedom or the n minus 1. It's the same number. This divided by 11. And then we need the square root, which is the actual results. Standard deviation is the square root of what we just got. 1.29. If we were going to use the formula, we need stdev dot s for sample. So we'll just highlight the values, and we should see it comes out to be exactly the same. From now on, you may use this formula. With that in mind, we can now go ahead and calculate what we need. Instead of using the norms_inv, we're going to use t_inv, which goes from alpha over 2, or a percent, to a t-score. Remember, a t-score functions exactly the same as a z-score does. It's the number of standard deviations. It just works on a t-distribution, whereas a z-score works on a normal distribution. So we need to use a t-score, and this will be equal to t_inv, and then we will put the 0.025, and it needs the degrees of freedom, 11, which gives us 2.59. Let's compare this briefly to the z-score. If we did a z-score, this would be norms_inv. Z-score doesn't care about the degrees of freedom or the sample size. We would just put in the 0.025. It's going to give us a negative number, but that's fine. I'll just put a minus out front to account for that. And we see that it's 1.96. Remember, for our empirical, we were estimating around 2. 1.96 is more precise. In any case, what we expected to happen happened. The t-score said, well, because the standard deviation that we're using is an estimate, let's be a little bit wider to account for that. And so our t-score is larger than our z-score is. We won't need the z-score for this problem, so I'll get rid of it. But we can see that it ended up being a smaller number than the t-score. And if we knew the true standard deviation, we could use the z-score on that. Since we don't, but we still want to be the same level of confident, we need our interval to be wider, just the way it works. So t of alpha over 2 came out to be 2.59. We'll also need to find our sample standard deviation for the distribution, which is the same deal. We need to take the original standard deviation and divide by the square root of the mean. That part hasn't changed. So we'll need to take this, the 1.29, divide by root 12. We can do that over here as well. And so that can be standard dev of means equal to our calculator standard deviation, by square root 12.3725. And then it's the same idea. Our error bound for the mean is going to be our t-score multiplied by the standard deviation we just calculated. So that'll be the 2.59 times the 0.373. We can calculate that in Excel. So EBM equal this times this, 0.966. And so then we can calculate the X min and the X max by saying it's going to be the mean minus the EBM and the mean plus the EBM. So our confidence interval is 8.02, 9.95. And once again, we'll want to interpret all of this. We are 95% confident that the true mean hours slept is between, and we can round for our interpretation, between about 8 and about 10 hours. Exactly the same as last time. We can even draw a very similar looking graph. Oops, let's do it over here. We can make some more space up in this area. There's the t distribution. There's our calculated mean. We're looking for 95%, which means over here we have 2.5% since it's on either side. This is the error bound of the mean. We've got our X min and our X max over here, which form the endpoints for our confidence interval. Let's do just one more example. If we have a proportion with a fairly large sample size, then the binomial distribution looks roughly normal. Remember, we said at least 30 would work. The mean for a proportion is equal to n times p, where p is the chance of success and n is the sample size. And the standard deviation is equal to square root of npq, q being the chance of failure. So we can treat binomial distributions as if they are normal and do a confidence interval the exact same way. For proportions, don't worry about t-scores. For proportions, we're making the assumption that the standard deviation we calculate is correct because it was so easy to calculate it using a formula. So we don't have to worry about our standard deviation not being quite right. And as a result, a normal distribution and a z-score is all we will need. Let's write down everything that we know. We know the sample size is 500. It says that 421 people said they did own an iPhone, which means that 79 said they did not. Our confidence level is 0.99, which means our alpha is 0.01, and we'll of course need alpha over 2, which is 0.05. remember once again what this means for our graph is that we've got 99% of the data in our given range, which means that 1% is outside of that range, split on two ends. So 0.5% is on each edge. And I just realized for our alpha, we should have had an extra 0. It should have been 0.005. We can use this, therefore, to calculate our mean and our standard deviation. Our mean is given by NP. So that will be, for P, this is not 421. It should be 421 over 500 because it's the proportion that was accurate. So we can plug that in. Let's make a new sheet. P equal to 421 divided by 500. So 0.842. And that means that Q, for Q, we can either do the same thing again, 79 divided by 500, or it's 1 minus the chance of success. So equals 1 minus this gives us out 0.158. If you would like, you can also record X to be 421. X is the number we counted that were successes. P is the proportion of those that are successes. So in this case, we need to calculate the mean and the standard deviation. The mean is equal to 500 times 0.842, comes out to be 421. The standard deviation is the square root of 500 times P times Q. 8.155. Let's write those both down. So square root NPQ. This gave us 421. Standard deviation, 8.156. Okay. Next, we can go ahead and perform the z-test, or the confidence interval with z-scores. We'll need a z of alpha over 2. So that's a z of 0.005. We'll plug that in. Z of 0.005. We need norms inf 0.005. And remember, we'll just record the positive version, 2.576. I'm even going to put in a negative up front because we want to turn it positive. We'll need the actual standard deviation for the distribution of means, which is, once again, the original divided by root n. So that will be standard dev for means equal to the calculated one divided by the square root of our sample size, 0.3647. For our EBM, that's going to be equal to the z-score, the number of standard deviations, multiplied by the size of the standard deviation. So that is 0.9395. And thus, the confidence interval will be, let's find the x-min and the x-max. The x-min is equal to the mean minus the error bound, and the x-max is equal to the mean plus the error bound. So our confidence interval is 420.06, 421.94. And once again, we'll interpret. We are 99% confident that the true, we'll say the true number of citizens in a 500-person sample who own iPhones has a mean between 420 and 422. We could find a confidence interval for the proportion by dividing each of these by 500. So if we divide this by the mean, or excuse me, not by the mean, by the sample size, so by the 500, and we divide this by the 500, then it tells us that our 99% confidence interval says that we're pretty sure that between 84 and 84.4% of citizens own cell phones. It was a pretty big sample size, which gave us a tiny standard deviation. The more people you sample, the larger the sample size, the more precise your measurements will be. That's what Chapter 8 is all about, constructing confidence intervals. And remember, we've got 3 scenarios. If it's a proportion, where we know we have a sample size and a chance of success, and it told us how many successes we have, then we use a normal distribution with the NP and Q to calculate it. If it's not a proportion, then we need to check and see if they gave us a standard deviation or if we calculated the standard deviation ourselves, which might be because they gave us data or might be because they told us what the standard deviation was for the sample. If we know the actual standard deviation, we'll use z-scores and a normal distribution. If we don't, we'll use t-scores and the t-distribution. But the process is exactly the same in all 3 cases. Find the z or the t-score using the inv function. Find the standard deviation by dividing by square root sample size. Multiply these 2 things together to find the error-bound mean. And then add and subtract this error bound from the mean to get our confidence interval. That's all we've got for today. See you next time.